everybody, this is Thomas Smith from Newton's Third Tutoring. Today we're going to be going over a topic in engineering dynamics. That is the topic of work and energy. So we're going to be going over a problem from R.C. Hibbeler, edition 13. It's 14-3 is the problem number, which is involving a crate here. So we'll go ahead and draw the problem out. We're going to go ahead. It's a couple of forces acting on a crate. We want to see what the distance the crate travels, given it some certain criteria, which we'll go over. So we'll have a crate here with 800 Newton force at a 30-degree angle on the rear edge of this crate, and on the front edge we'll go ahead and have a force, 1,000 Newton force with a 3, 4, 5 triangle here, denoting the different vector forces that we'll go ahead and break down. As well, we'll have a friction coefficient of 0.2. So with this crate sliding on the ground here, we'll have a friction coefficient of 0.2, which will be resulting in a friction force working against the crate. So we'll go ahead and go over the given information here. So we'll have a mass of 100 kilograms for this crate. And next we'll have an initial velocity of 0. So the problem states that the crate is at rest. So the initial velocity is 0 when an object is at rest. The final velocity at position 2 will be 6 meters per second. And again, we are looking for the distance that this crate travels. So we're going to go ahead and look at our work energy equation here. So work is defined as a force applied over a distance. And if you look in the chapter on work energy in Hibbeler's book, you'll see that the sum of the work done from position 1 to 2 is equal to the change in kinetic energy from position 1 to position 2. So this can be rewritten as the initial kinetic energy plus the sum of the work done on the object is equal to the final kinetic energy. And again, this is the sum of the work done on the object. There can be multiple different types of work. You can have work from a force, work from a spring. In this particular problem, we have only work done by a couple of constant forces, as well as the force of friction. The kinetic energy as well is equal to 1/2 the mass times the velocity squared. Going from one position to the next, the velocity obviously changes. We have those as givens, and as well the mass we have as well. It's a constant mass; it's not changing, so that'll be constant from each position. We'll go ahead and look at the work first. Again, this is the work done from position 1 to position 2. So the forces acting on this crate that'll over that distance are the 800 Newton force, the 1,000 Newton force, and the force of friction. We're not going to look at the force in the y direction because the crate isn't moving in the y direction; it's moving in the x direction. So we'll have to break down the forces into the x components. So the 800 Newton force multiplied by cosine 30 degrees, multiplied by, again, the distance. That's the distance from position 1 to 2. That's the work done by the 800 Newton force, plus the 1,000 Newton times 4/5 against the 3, 4, 5 triangle. So in the x direction, it's the 1,000 Newton force is 4/5 of the total force. And that's multiplied by the distance. And then this is minus the friction force, which is the normal force times the friction coefficient times the distance traveled. And that's a minus because it's opposing the direction of motion. The reason that the 800 and 1,000 Newton force is positive is because it's what's known as same sense. If the force acts in the same direction as motion, that is a positive work done on the on the object. We want to look at the normal force here. So the normal force that makes up the friction force is going to be the sum of the forces in the y direction. We'll go ahead and do the downward force as positive because normal force acts upwards. So we want to see what that equal and opposite force is. So in the downward direction, we have an 800 Newton force times sine 30. That's the y component, and that's acting downward. The 1,000 Newton force acts upward, so that's a minus 1,000 Newton force times 3/5 of the 1,000 Newton force. And again, we also have the weight of the object, and that's mass times gravity. So we have 100 kilogram mass times gravity, which is 9.81 meters per second squared. If you simplify this, you'll get 400 newtons minus 750 newtons plus 981 newtons. And if you go ahead and simplify this further, you'll get 631 newtons, and that will be your normal force that we'll go ahead and plug in to get our friction force. So looking at the work and simplifying the equation after plugging in everything, we'll go ahead and see what that looks like here. So we have 692.82 times the distance traveled plus 800 times the distance traveled minus 126.2 times the distance traveled. And the units here are newtons. It eventually will be Newton meter because it's obviously times the distance component. But at the moment, it's newtons. And so we'll go ahead and simplify that further. We'll get 1,366.62 times the distance traveled. And that's the work done. We'll go ahead and look at kinetic energy now as the other part of the work energy equation. As we stated before, the kinetic energy is equal to 1/2 times the mass times the velocity squared. The initial kinetic energy is 0 because we have a 0 velocity. So since it's at rest, initial kinetic energy is 0. Final kinetic energy is 1/2 times 100 kilograms times a final velocity of 6 meters per second squared. And that 6 meters per second was a given. And simplifying that further, we get 1,800 Newton meters is the final kinetic energy. So now that we've solved for the work and we've solved for the kinetic energy, we'll go ahead and plug all these variables in to our initial equation, and we'll go ahead and solve for the distance traveled. That's what we are looking for here. So we'll take another look at the equation. Again, this is the work energy equation. It's the initial kinetic energy plus the sum of the work done is equal to the final kinetic energy. Plugging in the values that we've solved for, we get 0 plus 1366.62 times the diameter, and that's in newtons. We want to make sure we're consistent with our units here. And that's equal to 1,800 Newton meter. And then solving for the distance traveled, we get 1.32 meters, and that's the distance traveled. So that's just that's again problem 14.3 in R.C. Hibbeler's 13th edition of Engineering Dynamics, going over work energy. I hope you enjoyed the video. If you have any questions or comments, please feel free to email me. Thanks for tuning in. If you'd like to hear more, go ahead and go to our website at www.newtonsthirdtutoring.com. And this is Thomas Smith signing off.